Welcome to the first lecture of this course on tectonics and geodynamics. This is a lecture, as I've said, will comprise 60, there will be 60 total lectures, and this is the first one of the series. So, it will roll as if it's a part of a story, and then from time to time the technical details when they come in, I will explain them as we keep rolling around. So, I hope you'll actually enjoy the course as you go through it, but we'll begin through this whole course on tectonics and geodynamics, right, starting from the beginning of the story. It is a story, it's a lovely story, and we'll begin with it. The first lecture will be on the beginnings of continental drift theory. So, how this particular theory originated, because this really was the theory that laid the foundations of how tectonics came to being. So, the beginnings of the continental drift theory, right. So, this is what we will be talking about. The story that we will be discussing will be dealing with this in particular. Now, this is just an image, a free image captured from freeworldmaps.net, so which actually indicates a map of the world. Now, what's interesting about this particular map is that when you look at it, you see that the Earth's surface, if you actually rolled it out into 2 dimensions, you'd actually see that it's a distribution between blue areas and green and yellow and red areas. Now, the green and yellow and red areas are, as we know, the continents, and the oceans in between, the parts that are occupied by oceans, are depressed with respect to the continents. So, the continents are elevated, the continents are the parts that we actually survive on. So, what we refer to as land in geology or in the earth sciences or in earth system sciences refers to the continents. Now, the continents, if you look at them today, right, so they are dispersed in more or less this manner. You can see that you have North America, right, round about right up here, you have South America, you have Eurasia, which is a combination of Europe and Asia, right about here, of which India today is a part. You have the continent of Africa, right, and you have this large island of Australia down here, and even further south, what seems to be enormously large is this continent that we call the Antarctic. Now, one of the things that you must know when we are looking at a 2D projection of any particular map is that when we look at the bottom of any map, it appears to be enlarged. This is simply a function of converting a spherical surface and projecting it in 2 dimensions. So, one of the projection schemes that is used, something called the Mercator projection, keeps all latitudes and longitudes at right angles to each other. As a consequence, place the parts that are near the pole, the areas on the surface of the earth that are near the poles actually appear to be larger than they actually are. So, this is really a function of the projection, but it is useful because it is easy for us to actually demonstrate things in 2D. So, this is the reason why we see this distribution. Now, this is what we see on the surface of the earth if it is projected in 2D. What would we see if we looked at it on the surface of the earth? Now, these are 2 images again captured from a free program that we all use called Google Earth, something that is very commonly used by everybody nowadays all over the earth. Now, if you look at it, if you looked at the earth from outer space, right, for the first time the people who looked at this were people on the moon who actually saw the earth completely as one round sphere from outer space, from the surface of the moon. Now, if you looked at the earth from outer space, there are 2 possible views you can get. Now, if you look from one side, right, I've deliberately selected this particular image because it has our country more or less in the central part of the circle that you see. So, this is one hemisphere that you are looking at, which has India, it has Eurasia, it shows most of Africa, but mostly it is it's Asia that is actually being shown in this particular part. However, if you look at the earth from another side, right, which is the image to the right, this one here. So, this particular image, right, shows what we know as the Pacific Ocean. Now, the Pacific Ocean is just to give you an idea of how large it is. So, it is possible to look at the earth from directly above the Pacific Ocean, and in that case you would hardly see any land areas at all. Now, this is just to give you an idea that the dispersion of land and sea on the surface of the planet Earth, right, is not uniform. So, essentially one hemisphere of the earth contains almost all the continents, whereas the other hemisphere is occupied largely by the Pacific Ocean, and even in the hemisphere which contains land contains a significant part of the oceans as well. Now, so the surface area of the Earth, 3/4 of it is ocean, right? Roughly about 1/4 of it is land. So that's the approximate distribution we have of land and sea on the surface of the Earth. The most important thing, we call this a crustal dichotomy. So the surface of the Earth is dichotomous. It has two types, right? So you have oceans and you have continents. So these are two things that we can see on the surface of the Earth. Now, the Earth is not actually unique in this, because there are other planets. For example, the planet Mars also has this hemispheric dichotomy. So the southern part of Mars, the southern hemisphere of Mars, is elevated with respect to the northern parts, which is a lowland area. So it is not, this dichotomous nature is not something that is unique to the Earth. But there are certain things that are, of course, very special to the Earth. And to understand this, right, why the Earth is, what the Earth is like and what the other planets might be like, right, it's good to have an idea of what lies inside the Earth. Now, since you've all, most of you are master students who've done some course or the other of the Earth, so the internal structure of the Earth must be something that is known to you. Now, the Earth, as you know, has three broad layers, the three major layers. The first layer, the outermost layer, is actually the thinnest one. This is the crust, right? That's the one that's here. Now, the crust itself is very thin. Now, I've marked it out as 70 kilometers, but that's actually the thickest, almost the thickest part of the crust. The crust normally is much less than 70 kilometers. It's exaggerated to sort of keep parity with the rest of the diagram. Now, inside there, separating the crust from what is there below, is something called the mantle. Now, both of these parts, the crust and the mantle, these are silicate in composition. So these are silicates. And between them, the boundary between them, that is, we are talking about this particular part here, right? This boundary itself is called the Mohorovičić discontinuity, or in short, we just refer to it as the moho, right? So this is the moho. So it's essentially the interface between the crust and the mantle. Now, as you go further in, right, the silicate part of the Earth now passes into what's called the metal phase. Now, the core of the Earth, right, which lies at a depth of around 2,900 kilometers, this core of the Earth, right, is separated from the mantle, right, by this particular discontinuity here. This part is called the Weichert-Gutenberg discontinuity. Now, just like the boundary between the crust and the mantle is actually a compositional interface. There are phase changes, of course, but importantly, there is a major change in the chemical composition. Likewise, there is an even more drastic change when you go from the mantle into the core. Now, the core itself is metallic. So it's a part which contains little or no silicon. So it's essentially an iron-nickel alloy with perhaps one other light element or more than one other light element inside. But the major part of it is iron and nickel. And that's why the core of the Earth is much denser than the silicate part of the Earth. So the very high density of the Earth, which is around 5.5 grams per cc, it actually results because of the presence of this very dense core. Now, the core of the Earth itself, right, it's quite large. So the radius is around 3,480 kilometers. The core itself, right, is separated. The outer part of the core is separated from the mantle by the Weichert-Gutenberg discontinuity. And then, as this part itself is a region which is, as you know, is liquid in nature. We think that it is liquid because the shear waves, the seismic waves which actually pass through the interior of the Earth, these cannot pass through the outer core of the Earth, which tells us that this is actually liquid in nature. So this is an iron-nickel alloy. Interestingly, at a depth of around 5,000 kilometers from the surface, that is this part here. So if you go down from here to here, this is roughly around 5,000 kilometers. This particular interface, right, that you see, this is called the Lyman discontinuity. It's called the Lyman discontinuity. Now, this is important because it actually separates the outer and the inner core. Now, the inner core, which is this part, is actually solid. and the outer core is liquid. We believe that they're both more or less similar in composition, which means that at this depth, right, at 5,000 kilometers, it's essentially a phase change between a liquid metal, iron nickel alloy, and a solid metal, which is also an iron nickel alloy. So it's actually one of the things that tells us the temperature of this particular interface, because it must correspond to the melting point of this iron nickel alloy at that particular pressure. So if we actually know what this pressure is, we can do experiments, or we can apply certain thermodynamic principles to try and predict what the temperature would be at the core mantle interface. Now, this figure, the temperature of the interior of the Earth, there are a lot of assumptions based in in estimating what these are, and our ranges likewise have large errors, but we think it must be somewhere between 4,500 to 7,000 Kelvin. So that must be the temperature of this particular interface, right? So the Lehman discontinuity. Interestingly, Lehman was a lady, and she was the one who actually discovered this, right? As a result, she was a seismologist, and she actually interpreted some very complex data and was able to tell that what we're looking at is actually the interior, a solid core in the interior of the planet. Now, though we will talk about this later, this presence of a solid inner core and a liquid outer core is actually responsible to a large extent for the magnetic field of the Earth, and this is actually demonstrated. This record of magnetism is preserved on the surface of the Earth, and as we will see, this has been instrumental in us understanding what's going on at the surface of the Earth. Now, just to break up what this internal structure tells us about the interior of the Earth. So we have a continental crust, which has the average composition of a rock called granodiorite. The density is around 2.7 grams per cc. This includes both the upper part and the lower part of the crust, which are believed to be slightly different in composition and density. The oceanic crust, right, comprises two parts. The upper part is volcanic in nature, which is a basalt, and the lower part is the volcanic equivalent of the basalt, which is called a gabbro, and its density is slightly larger than that of the continental crust. It's 3 grams per cc. The mantle itself is made up of a rock. The mantle just below the crust is made up of a rock called peridotite. Now, this is mostly made up of ferromagnesian silicates, and it's got a very high density from 3.3 to 5.7. Now, I must caution you that this term peridotite is the name of a rock. Now, a rock is described as an assemblage of minerals. Now, inside the mantle, the minerals that make up the rock called peridotite only survive till about 400 kilometers into the interior of the Earth. As you go below 410 kilometers, the composition of the mantle remains, the chemical composition remains roughly the same. However, what does differ are the minerals which make up that rock. And because the minerals differ, below 400 kilometers, technically, we should not be using the term peridotite anymore, because the minerals that make up a peridotite, for example, olivine, one of the most important minerals that makes up a peridotite, is not present below 400 kilometers. So the mantle itself, the chemical composition, right, it keeps on getting denser. It undergoes phase transitions till you actually go to the Gutenberg discontinuity, after which you have this iron nickel alloy, which is iron with about 12% sulfur, silicon, oxygen, nickel, and potassium. Now, it's a guess between different workers as to which one is the light element inside the core, but the average density of the outer core is between 9.9 to 12.2 grams per cc. Similarly, the inner core itself is also believed to be similar in composition. We have fewer constraints on the inner core, but nevertheless, we know that its density must be roughly between 12.6 to 13 grams per cc. On an average, what this means that if you take all of this together, the average density of the Earth is 5.5 grams per cc, right? And in fact, it's actually the densest planet. Now, let's take a closer look at the crust mantle system itself. And as I told you that we have two types of crust. We have an oceanic crust and we have a continental crust. Now, the ocean crust varies between 5 to 12 kilometers thick. Now, this diagram, as you can tell, is grossly exaggerated. Now, the thinnest continental crust we know of, which is elevated, which is above the surface which is above sea level, really, is around 20 kilometers. You can have thinner continental crust, but that would be submerged. To a maximum, there are places where we think that the continental crust could be about 95 kilometers thick, but more or less the thickest part, which is essentially below large mountain ranges, is of the order of between 80 and 90 kilometers. Otherwise, on an average, the crust, the continental crust, is around 35 kilometers thick. Right? So, just around 35 kilometers is the average thing that you see in what we call continental shield areas, right? A part which is more or less stable thickness. So, the oceanic crust is much thinner than the continental crust. That's the first thing to note. Now, as you go deeper into the mantle, now there are two parts that's important. What seismologists tell us is that as you proceed into the mantle, seismic wave velocities increase, and this is interpreted to reflect the increasing mechanical rigidity of the material that makes up the Earth's mantle. So, this part of the Earth's mantle, right, the part that's immediately below the crust, this is the part that is actually very stiff. The seismic wave velocities keep on increasing till you approach a depth of around 70 to 100 kilometers below the oceans, and 150 to perhaps even as much as 300 kilometers. It could be as much as 300 kilometers also below some parts of the continents. You have an extension of this very rigid part. Just below this is a zone where seismic wave velocities show a drop. Now, this is reflected, the interpretation of why they drop, right, in terms of what material makes it up, are numerous. We won't go into that right now, but what's important to note is that it indicates that there is a change in the mechanical behavior of the material that makes up the mantle. So, this part of the mantle just below this particular interface that I am showing here, right, this interface, just below that, that part is actually fluid, it's more plastic in nature. So, this is a part that can flow, unlike the part that's on top, it's too mechanically rigid. So, there is a change in rheology as you cross this particular interface. And then when you cross 660 kilometers, once again we believe we pass into relatively rigid mantle. It's not completely rigid, but relatively rigid, because at those temperatures, the temperatures are very high in these regions, we believe that most material would be plastic. Now, it's important at this stage to understand, right, the difference between the crust and the mantle, and two new terms that I'm introducing, the lithosphere and the asthenosphere. Now, the crust and the mantle, right, are defined compositionally. So, you have the Moravecik discontinuity, which separates material that is peridotitic, right, from material that's on top, which is more silica rich, which is the crust, which could be ocean crust, could be continental crust. However, in terms of their mechanical properties, the strength of the material consistently increases down to this particular interface. So, this part, which comprises all of the crust and a part of the upper mantle, this is a rigid outer part of the Earth's skin, you could say. We refer to that as the lithosphere. And the part that starts from what's called the seismic low velocity zone, the part where materials get weaker, and continuing down to around 660, we refer to that part as the asthenosphere. So, this part is supposed to be mechanically much weaker than the part that's on top. So, essentially the lithosphere itself, the crust and the mantle in these upper parts, this part and this part, are mechanically coupled together. That's the model. And we believe that the uppermost part of the mantle and the crust together, they comprise the lithosphere. They are strongly mechanically coupled. This has thermal consequences of the manner in which these two parts, that is the asthenosphere and the lithosphere, how they actually transmit heat also differs, varying depending on this. Now, let's just go a step further then. There is a difference between, there is a difference between the continental and the oceanic crust. Now, what are the differences? It's good to remember what these differences are, because these are absolutely key to what we are going to understand. So, the continental crust is less dense than the oceanic crust. The continental crust and the oceanic crust are different in composition. The continental crust is granodioritic, right, which is more silica rich, whereas the oceanic crust is more basaltic, which is much less silica. The continents are thicker than the oceans, and of course we know that the continents are more elevated than the oceans. That's why we survive. That's why I'm giving this lecture here. Also, it's important to know that continental crust can be very old. It can be very new, but it can also, parts of it can be very old. It can be as old as 4 billion years. Whereas all oceanic crust that we know of, right, is less than 200 million years. So, now if we look at this, there is a significant difference between the two types of crust that make up the outer surface of the Earth. Now, if we compare this to other planets, for example, Mars, Venus, and Mercury, what we know of their surfaces is that most of these are covered with basalts. There are very few acidic rocks which correspond to the compositions of the Earth's continents. The Moon, for instance, Moon also has a dichotomy. So you have highlands and you have lowlands, which are the dark patches that you see on the Moon. The dark patches are basalts. The light patches also are not acidic rocks. They're not continents per se. They're a rock called anorthosite. So acidic rocks, the rocks that make up most of our continents, these are very few, even on the Moon. So in that manner, the Earth itself is unique. You have a significant proportion of granitoids in the Earth's crust, and these are the granitoids that make up the Earth's continent. And it's important to know this is why the Earth is such a unique planet. Now, even within the crust, right, the continental crust. Now, as far back as the 19th century, this famous gentleman called Edward Suez, he actually suggested that the continental crust was made up of two different layers. Now, he suggested this on the basis of the chemistry, the geochemistry. And he suggested that the Earth's crust was made up of an upper part and a lower part. The upper part was lighter than the lower part. The upper part was dominated by silicon and aluminium. The lower part was dominated by silicon and magnesium. Now, the upper part's density, because aluminium is lighter than magnesium, right, it's about 2.7 grams per cc, and the lower part, right, is around 2.9 grams per cc. Now, the boundary, right, which corresponds approximately to a density of 2.8 or so, it's been identified seismically in some parts of the Earth. Now, I must mention that this is not, it's not the case everywhere. The Conrad discontinuity, as it's called, is not detected everywhere in the continents, but it's there in many places, and we believe there that there is a difference in the velocities which is consistent with a density change across like this between the upper and the lower parts. Now, we call it the Cl, taking silicon and aluminium together, and the lower part called Cma, taking silicon and magnesium together, right? So these are the two parts which form an important component of what we're going to discuss in the context of continental drift. So if you look at a schematic diagram which actually indicates this, so we have the continents, right? So the continents are there. This thick black line is the moho, and we have an upper and lower part of the continental crust. The upper part of the continental crust is the part that's called the Cl, and the lower part is the Cma, and this is their interface. So you can actually call this your Conrad discontinuity. Now, the oceanic crust, the ocean and the continent transition somewhere around here. It's in a place called the continental rise, right? After that, right, we have to go in now to look at what the theory is based on. We've seen that the continents and the oceans, they actually look different. And as far back as 1620, right, a very well-known thinker, his name was Francis Bacon, he formulated something called what we now call empiricism. So he argued for using scientific knowledge, right, through a reasoning process. Now, this is something we refer to as inductive reasoning. He documented all this in a book which is written in Latin. It's called the Novum Organum. And this method that he advocated, we now call it the Baconian method. Now, it's a scientific method. Now, this, he mentioned it specifically. He mentioned that this was providing two directions concerning the interpretation of nature. Now, what this actually means is that we are now trying to interpret nature, right, in a scientific way, in a logical manner. And this was the first beginning, really, of looking at natural sciences scientifically. So Francis Bacon is really very much regarded as the father of looking at natural sciences and scientific thought. Now, the first thing that Francis Bacon actually noticed is, I mean, at that part, already by that time, by 1620, we had a crude knowledge. The Americas had been discovered. And the first thing that he asked us to notice is to look at this. Now, even at that time, the cartographers had managed to see that if you look along this margin of South America and say this part of Africa, you notice that it's a remarkable jigsaw fit. So you can actually take this red line, and if you move it out to here, then you can actually fit the eastern coast of South America, right, into the western part of Africa. And it's a beautiful fit that way. Now, Francis Bacon was the first person to note this correspondence, this match of the coastlines. He was the first one to note this. And even at that time, in 1620, he said that this similarity cannot be accidental. So he thought that there must be some kind of science in it. Otherwise, this was really too much of a coincidence to just leave out to fate, that it just happened. And this really was the beginning of what we call the continental drift theory. Now, after Bacon, in 1668, right, a Frenchman, Francois Placé, he wrote a memoir. He also suggested that the old world, which is Europe at that time, and the new world, which was the Americas, which had just been discovered, they had been together at one time and they were separated following what he called the flood. Now, what was this flood? Now, the flood, you must remember that at that time, the European world was very strongly governed by biblical thoughts. So it was really something that was the answer to all knowledge that man had ultimately. And the flood is something that is referred to in the Bible, right? It's a famous and a beautiful story about how a lot of sin was permeating the earth, and so God, to actually get rid of all of that, he actually made it rain for 40 days and 40 nights. And he just asked one particular virtuous person called Noah and his family to save the world and save 2 animals of each kind so that they could actually, the race progeny would continue. So that flood, the massive flood, is something that is referred to in the Bible. And what Placé thought was that the old and the new worlds were actually separated following the flood. Now, around 1800, a famous person, now he's very well known to the Indo-German community, Alexander von Humboldt, right? He was a pioneer explorer of Mexico and in the United States. And he also thought, he noticed this, that both parts of the Americas, right, they had these signs which were similar. And he suggested that there was a great volume of water. He suggested that the whole of the Atlantic Ocean was actually not ocean at all. It was a huge river valley. And this has been separated by this huge volume of water over which Noah's Ark had sailed. So he had actually taken Placé's thought and incorporated into it. Now, Noah's Ark is the name of the boat on which Noah survived with his family for 40 days and 40 nights before he actually landed in something called Mount Ararat, right, in the Middle East. So this knowledge, right, that the 2 sides of the Atlantic were similar was known since that time. Further on, just a little further on, 1858, another person called Antonio Schneider, right, of France, he gave the first diagram in which he had the courage to actually pull the continents together, and he showed Europe attached to North America and South America attached to Africa. And he tried to show this in a diagram that he published in 1858. Now, this book of his, written in France, in French, this showed that the continents bordering the Atlantic were together. And he had additional evidence. He noticed that there were similar fossil plants which were seen both in Europe and North America, and in particular types of coal deposits. So the plant fossils that you saw on the coal deposits of Europe and North America were similar. So he used that as evidence. Then in 1878 to 1879, we had this famous name coming in, Darwin. Now, he wasn't Charles Darwin, but he was related. He was his son. George Darwin was an astrophysicist, astronomer, and he first proposed, along with his friend Osmond Fisher, that the moon of the Earth actually originated, right, from inside the Earth. It was thrown out, and the gap that was left is today's Pacific Ocean. And this was, the Earth was spinning as the moon went out from its part, right, and it was drawn off. Why did it was pulled out? Because there was a passing star whose gravitational attraction pulled this material out from the center of the Earth. Now, Osmond in 1882 took this a step further. He said that when this happened, when the moon actually separated, right, from the Earth, that is when the Pacific Ocean was created, and that was what was the driving force to actually move the continents apart and provide the new shape of the Earth as we know it today. So this was the first suggestion that the origin of the moon was related to what we now call continental drift, or the movements of the continents. So now we're at the end of the 19th century. So let's just put all this information together. What does it tell us? Now, from as far back as the 17th century, right, in the 1600s, people had noticed this extraordinary match between the coastlines of South America and East Africa. By the middle of the 19th century, people had noticed that there were plant fossils and coal deposits which were similar, both in Europe and North America. Now, much of the scientific evidence, as we know it, for these continents, that these were joined, right, this was based, however, on stories that were derived from the Bible. There were a few theories which were so to say scientific in nature. These suggest that the moon was the moon, right? It actually was responsible for causing this movement of the continents on the surface, and this had already been proposed by the end of the 19th century. So the 20th century was going to see big differences, and that is what we will talk about in the next lecture. So these are the references more or less of the things that I've been talking about today, the story, and we'll continue the story in the next class. Till then, thank you.